Hello everybody. In this tutorial, we're going to do a modal analysis on a structure to determine the natural frequencies of the assembly. Let's get started. If this is your first time using Discovery, please go through this useful information on the welcome screen that helps you understand things like navigation, selection, using different tools, getting help, and so on. If you're done with those, you can just click here to dismiss the welcome screen and expose the home screen. In the home screen, click on Browse and Open Geometry File. Navigate to the appropriate folder, select the geometry that you want to import, and click Open. Okay, this is the geometry we're going to use for this tutorial. Now, this tutorial has two parts. In part one that you're watching right now, we're going to use the Explore mode to run this simulation using the proprietary Ansys GPU solver. Okay. In part two, which you should watch next, we'll do the same thing using the Analyze mode, using our flagship CPU solvers and turning on additional physics controls. Okay, first thing we want to do is apply a fixed support. So Control select these faces. And then click here to expose the halo, and then here to open the structural support tool. So we want this to be a fixed support, so click the green check mark to accept that. Now, when you're done applying a condition, you can always dismiss the heads-up display by hitting escape 2 times. Okay. Now we'll do the same thing for this bottom green bracket, but we're going to do it a slightly different way. Down at the bottom, you'll notice an advanced selection option. Click here and then make sure the power select option is turned on. Then select this face. You'll see now you have the option to choose all holes equal to 5 millimeters in this bottom bracket. Okay, you can collapse that. And then similarly, just expose the halo and apply a fixed support down here as well. Okay, and then let's hit escape 2 times to dismiss the HUD. You'll notice when you do this, on the physics tree on the left, you have fixed support 1 and fixed support 2. Okay, the next thing we want to do is Control select these two faces and then apply a mass. Okay, so we're going to use a value of 2 kilograms, but we're also going to use a remote point. So here you can specify coordinates of where the centroid of this mass is going to be located based on the global coordinate system. Now you'll notice, for convenience sake, in this geometry, the global coordinate system is located right in the center of the two faces that we selected. So the values you want to use are 0 for x, 0 for y, and then let's say 200 millimeters in the z direction. So you can just enter the number 200 and then mm and then hit enter, and it automatically converts that to meters. So if I zoom out a little bit, you'll see the location of that remote point that we want to use for this mass. Okay, so let's hit escape 2 times to dismiss the HUD. Okay, at any time, if you want to change these inputs, you can just double click in the physics tree like so, and it will launch the heads up display again. Another thing I want to point out is you can hit F1 at any time to enable the overlay help system. This is a very handy way for you to understand what all these different icons mean and so on. Hit F1 again to dismiss the overlay help system. Okay, we're done with our boundary conditions. We're going to assume structural steel is okay. Of course, you can change the material properties if you want, but in this case, we're going to just assume structural steel. And we want to do a modal analysis or a natural frequency type analysis. So to turn that on, click here. Okay, you'll notice down in the SID or simulation information display, a little icon shows up which indicates that this is a natural frequency or modal calculation. Okay, so that's really all you have to do. So let's click the green solve button to get our answer. Now we are using our real-time GPU solver, so you'll see results almost instantaneously. One thing I want to point out that for a modal analysis, it takes a little bit longer to get all the results. So what you see displayed on your screen is contours of displacement for the first mode. So you can click here to kind of exaggerate the deformation. You can click here to show the animation while the solution is still running. Now you'll notice down on the SID, we have a green line, green color all the way around, but we also have this kind of white line which is kind of moving its way around. This shows that the computation is still being performed. And when that green line stops moving, I'm sorry, the white line stops moving around, you know the solution is done. You'll also notice the different modes will be available for you at the top of the legend. And you can see that happening right now. So you see mode 1 is calculated, and mode 2 and mode 3 and so on. So let's just wait a couple more seconds for this to be done, and we'll be able to visualize the deformation and frequencies at the 6 modes that were just calculated. So there we go. All 6 modes have been calculated. So click on mode 2. This shows you the mode shape for the second mode along with the frequency in Hertz. You can see the same thing for mode 3 and mode 4 and so on. So if I go back to mode 1, I want to point out that in Explore mode, the solver assumes that any bodies which are touching are fully bonded or glued together. So this result that you see on the screen is valid only if the bonded assumption is valid. So you have to use your engineering judgment to decide whether this makes sense or not. In the next video, we're going to show you how you can apply local contact control to more accurately define the way these bodies are connected together. Okay, so there you have it. Very quick and easy way to do a modal analysis or natural frequency calculation using a couple of fixed supports and a remote mass. So this ends part 1 of this tutorial. Please make sure you watch part 2, where we will go into more detail in analyze mode, including things like local contact definition and so on. Thank you very much.